This video is about relays. Sometimes in areas like home automation or in control circuitry, it's very useful to allow a very small source to switch on and off very large amounts of current. For example, you might want to switch a light fixture on and off using the output of a microprocessor or the output of a computer. You might want to switch off very large motors using only very small signals. You can do that with transistors, but you can also use relays. And a relay is a type of switch. I'll describe how it works here in a moment, but the advantage of a relay is that it offers perfect isolation between the switching circuitry and the circuit that you're trying to switch. So you could say that it's a very safe way in order to switch large amounts of current. Let me show you how a relay works first of all. Imagine that we have a coil of wire wrapped around a piece of iron, and that coil of wire is connected to a switch and a small voltage source. I'm showing here a 5-volt source, but you could also imagine that this is the output of a microcontroller or a microcomputer, where the voltage on the lines or the output pins typically 0 to 5 volts. This coil switch could merely be the output switching itself between 0 and 5 volts in response to a computer program, for example. In any case, when the switch is closed, we're going to create an electromagnet here. When the switch is open, then the magnetic field will collapse. This forms the principle of relays. Imagine now at the end of that electromagnet that we have something that's going to be attracted to that magnet when the field is energized. What we're showing here is a small contact that's free to move either up or down. If it moves down, then it's going to spring back up once the magnetic field collapses. You can see that in this particular configuration with the coil switch open, there's no contact between the point and the little piece of metal. But once I energize the coil, that's going to flap down and make contact with the point, completing the high voltage circuit to the load. This is the principal operation of a relay. Let's see what happens when I close the switch. When I close the switch here towards the left, the relay action takes place and completes the circuit between the high voltage source and the load. Once the coil switch is released, then the circuit on the high voltage side is going to be broken. Relays that you might find in circuits are typically not very large circuit elements. For example, this little orange box here is an example of a relay. There are two different types of relays that you would typically run into: non-latching and latching. Let me tell you what the difference is between these two different types of relays. The kind of relay that I just talked about is an example of a non-latching relay. Here's what the typical pinout would look like for a non-latching relay. This is from the data sheet of a relay that we're going to build a circuit with in just a few moments. The distinguishing feature of a non-latching relay is that when a voltage is not applied to the coil, the relay will spring back to its non-energized position on the high voltage side. For example, if I attach a load between pins 4 and 5, then it's going to be open until I apply a voltage between pins 1 and 12 and energize the coil. But once I remove that voltage between pins 1 and 12, pins 4 to 5 will move back to its non-energized position, which is shown here in the diagram. Let's now look at the action with a latching relay. With a latching relay, the circuit symbol, or the pinout, is nearly the same as in the case of a latching relay. The difference, however, is that when I apply a voltage between pins 1 and 12, and if that voltage is high enough in order to get the switch to change between pins 4 and 5, then it will stay changed. The circuit will remain closed on the high voltage side, even when the field is removed between pins 1 and 12. If I want to turn the circuit off in a latching relay, I actually have to reverse the voltage to the coil, or in this particular diagram, reverse the voltage between pins 1 and 12. That's why two polarities are shown: set and reset. In a moment, we're going to build a couple of relay circuits. We'll be building one circuit with a non-latching relay, and then we'll be building a circuit with a latching relay so you can get a better understanding of the differences between the two. First, however, let's take a look at a data sheet which is typical for a non-latching relay. It's nearly the same as it would be for a latching relay. Let's zoom in just a little bit and look at some of the key parameters for relays that you might find on a datasheet. First of all, the coil voltage is a key parameter. This refers to the voltage necessary across the coil in order to get the relay to switch. If the voltage is not high enough, then the relay is going to have trouble switching. Of course, the switching voltage on the high side is also important. This is typically a line voltage. It could be lower than this, but the highest value is what's shown here on the data sheet. We're here in Singapore, so our line voltage is 230 volts. This relay will certainly work. The third key parameter on the data sheet of a relay is the switching current. You could imagine that if you put too much current through the relay on the high voltage side, then because the wires are so small, you could burn it up. So this current is actually a very important parameter, and you want to make sure that not anything more than that current is passing through the relay. When we design our relay circuit here in a moment, we'll be putting a fuse in series with the relay to make sure that a safe amount of current is always flowing through the relay. We want the fuse to burn out before we want the relay to burn out. Otherwise, if a relay were to burn out and the contacts were to hypothetically fuse together, that could be very bad, because if we send a signal to turn a circuit off or to turn a voltage off at the high side, if the relay is burned out, it might stay on, and we don't want behavior like that in a circuit that we want to engineer well. Let's go over the circuit that we're going to put together here with the non-latching relay and do some calculations. This shows what the pinout of the relay looks like on the bottom. This particular relay has a couple of different switches inside of it. We're only going to be using the top switch here in this relay. There's another switch here on pins 8, 9, and 10 that's activated at the same time as the switch between pins 3, 4, and 5, but we're not going to be using it in this particular circuit. Although a relay is just a switch, you might notice here that we have 3 different pins, 3, 4, and 5, so where's the switch? Well, there's 2 different configurations here, the normally off configuration and the normally on configuration. We're going to start here with the normally off configuration. The normally off configuration is the configuration between pins 4 and 5. It means that if there's no voltage on the coil between pins 1 and 12, the circuit between pins 4 and 5 will be switched off. If I apply a voltage across my coil, then the switch is going to move right here, turning the relay on. It will turn it off between pins 3 and 4. Between pins 3 and 4, we have the normally on configuration. The reason why you might have a normally off configuration and a normally on configuration is because sometimes you might want the circuit to be on most of the time, and then you can apply a control voltage in order to switch something off temporarily. The normally off configuration, however, would be off all the time unless you apply a voltage across the coil. We're going to be switching off a lamp in our example relay circuit, and we're going to be using the normally off configuration. One thing that's important to keep in mind is that you always want to install a relay, or any switch for that matter, on the hot side of a circuit. You don't want to switch the neutral side of a circuit on and off. Light fixtures, which are installed in rooms everywhere in the world, are switched on the hot side of a circuit only. Relays should also be installed on hot sides of the circuits for the same reason. I'm also showing a fuse here, and you always want the fuse upstream of everything else in the circuit, so that if the current were to be too much, the fuse would blow out on the hot side of the circuit first. We know from the data sheet that this particular relay can handle up to 2 amperes of current on the hot side. We need to make sure that the wire we're using is thick enough to handle up to 2 amperes of current. Using the wire gauge chart from Wikipedia, we can see that we need to use wire thicker than about 24 gauge. So when I build circuits with this particular relay, I'll make sure to use wire that's thicker than 24 gauge. We also need to calculate the rating of our fuse. We know that in Singapore, we have 230 volts RMS coming out of the wall. If we know the wattage of our light bulb, we can calculate how much current is going to be passing through both the fuse and the relay when the hot side of the circuit is turned on. For example, let's say that we want to use a 60-watt light bulb. That means that 261 milliamps of current is going to be passing through our fuse and our relay. No problem. If we were to instead use a 100-watt light bulb, then 435 milliamps of current would be passing through our fuse and relay. The light bulb that I'm actually going to be using, though, is only an 18-watt bulb. It means that only 78 milliamps is ultimately going to be passing through our fuse and relay. I happen to have some 300 milliamp fuses on hand, rated for the line voltage here in Singapore. Those would hypothetically be enough to handle a 60-watt bulb, so these should be fine for our purposes here. In the demonstration, I'm just going to use a 5-volt source from our bench. I'll just be turning this voltage source on and off, and then we can see whether the light bulb switches on and off as we expect it to with the relay circuit. If I wanted the light bulb to be on all the time, unless I apply voltage across the coil, then I could wire it up this way. I'm not going to do this in our demonstration, but I just wanted to show how you would wire up the circuit if you wanted the light bulb to be on most of the time and then switch off when you apply a voltage across the coil. The latching relay has the same pinout as the non-latching relay, but the functionality is just a little bit different. This is the second demonstration circuit that we're going to be building here in a moment. If we don't have any voltage applied across the coil, then the light's going to be off. As soon as I apply 5 volts across the coil, however, the light bulb is going to switch on. If it were a non-latching relay and I were to get rid of the 5 volts across the coil, then the light bulb would immediately turn off. But with the latching relay, the light bulb will stay on even when the voltage is removed. If I want to get the light bulb to turn off, I actually have to apply a reverse voltage across the coil. If I then remove the reverse voltage, the light bulb will stay off. You could think of a latching relay as being sticky. The switch will stay in whatever position it currently is in until you apply either a forward voltage or a reverse voltage in order to get that switch to move. Whereas with the non-latching relay, it'll spring back into its home position when the coil's not energized. Let's go over to the bench now and demonstrate circuits with both the non-latching relay and the latching relay so you can see these circuits in action. I've built both of the circuits here at the bench. We have a latching version and a non-latching version. These circuits are both the same. The only difference is the kind of relay used in the circuit. You might have noticed that I'm using a perf board here rather than a breadboard in order to implement these circuits, and the reason for that is because it's dangerous to put high voltages or line voltages on a breadboard. Something else I've done here on the perf board is that I've arranged it so that we have a low voltage side and a high voltage side. So the low voltage side here will be hooked up to our DC power supply, and that will provide us the 0 volts or the 5 volts needed to switch the relay on and off. And then the high voltage side over here will be connected in series with our line voltage or the plug going into the wall and our load, which in this case is the lamp. So we'll start off here with the non-latching version of the circuit, which I already have wired up. Now, we don't have the high voltage side of the circuit plugged into the wall yet, so everything is still really safe here. The first thing I'm going to do is to use our DC power supply here to power up the coil. And what I'd like for you to listen to is the sound the relay makes as it hits the voltage at which the relay is going to switch. So I'm going to increase the voltage slowly, and when we reach some voltage, probably not quite at 5 volts, we should hear a little click sound as the high voltage side of the circuit switches on. Let's listen for it. I heard 2 clicks. It looked like it clicked on at about 3.6, 3.7 volts, and then when I rolled the voltage back down, it clicked off at about 2 volts. Let's try it one more time. We'll again listen for 2 clicks. All right, now what I'm going to do is to plug in the high voltage side of the circuit, and we'll use the low voltage side to switch the lamp on and off. There, the coil is now energized and the lamp is on. When I roll the voltage back down, or if I switch off my DC power supply right here, the lamp should switch off. Let's turn the voltage down. So we see it's clearly a non-latching relay. When the coil is de-energized, the lamp switches off. And I have it in the normally off configuration because when the coil is not energized, the lamp is off. I'm now going to take this circuit apart and wire up the latching version. So now I have the latching version of this circuit wired up here to the perf board. I'm going to start off by doing the same experiment that I did with the non-latching relay. I'm going to turn the coil voltage up until we hear a clicking sound from the coil, and then I'll turn the coil voltage back down. I didn't hear any clicks at all from this relay, which must mean that the relay is latched into the opposite position. Let's reverse the polarity and then turn the voltage up again and see if we can make it click in the opposite direction. I heard a clicking sound from the relay as I was increasing the voltage here, but as I decrease the voltage, we will not hear a clicking sound. Listen. The relay stayed in its position. All right, that's the key difference between the latching relay and the non-latching relay. I'm going to go ahead and put the coil polarity back to the way it was before. I'm now going to plug in the high voltage side of this relay circuit. The coil is still energized. Now watch what happens if I completely turn off my DC power supply. The lamp is still on. I hope you've seen now the difference between the latching relay and the non-latching relay. What do we have to do to turn the lamp off? Well, what I need to do is apply a reverse voltage on the coil of this relay. In order to do that, I can just reverse the polarity here at the input side of my relay and then apply a voltage. As soon as I energize the coil here, the lamp should switch off. We've learned the difference between latching and non-latching relays. Hopefully you've seen how useful relays can be in projects related to home automation and control circuitry. You might find relays useful in your own projects as well. This video is part of an organized sequence where I explore various AC and switching circuits. If you enjoyed it, then you might consider following the channel's playlist to learn more about these types of circuits.